All right, hello everyone. I think we might as well get started. If more people are arriving, then just please come in. But I think I might as well start on time because I have a lot of stuff to cover. So thank you all for coming. My name is Mark Seemann. If you want to know more about me, there's an about page there on blog.plur.dk. I should somehow see if I can get rid of that mouse pointer there. Excuse me. No? Let's see if that works. No, you just have to live with that. Let's see if I can put it down here somewhere. Okay, now you don't see it. All right, I'm also on Twitter @plur if you think that's interesting. I think Twitter is quite useful actually, so I'd love feedback there. So I'm going to talk about functional architecture today, and specifically about these things called pits of successes that I'm going to cover in just a moment. And if you're here and maybe you're a little bit afraid that I'm going to talk about a lot of complicated, sophisticated things, well, to a certain degree I am, but I'm also not going to assume that you may have heard about those things, and I'm also not going to assume that you already know how to read and understand F# code or Haskell code. So even though I'm going to show you a little bit of code, I'm not assuming that you actually know how to read that. So don't worry about that. I'll talk you through the important points of that. I'm also going to show you a bit of C# code. I assume that you understand that. So with that out of the way, let's just get started with talking about the pits of successes. So imagine that you have some sort of goal that you need to reach in your software development project. And I'm not only just talking about some sort of feature that you need to implement, but you may have a higher goal of saying, I want to enable my code base to be flexible and maintainable and all of those things while I deliver features. And I want it to be long-term maintainable so that I can also deliver features requested by my business 3 years from now, and not go to my stakeholders and ask for a rewrite, which happens quite often. So that's the sort of things that I'm going to try to talk about today, because that is basically what software architecture is about. Those sorts of decisions, also about scalability and all sorts of other things and so on, but all of those things that are actually what we call non-functional requirements. So you could imagine that you envision that goal as having to be, roll a boulder up to the top of a tall hill. So if you've ever studied, physics, just classical Newtonian mechanics, you'll know that if you have to roll a boulder on top of a hill, you'll need to exert some force in order to get it there. So you'll need to expend a lot of effort to actually roll the boulder up the hill. And if you are, able to actually roll it all the way on top of the hill, you can put it there. And if you're very, very, precise in doing that, you may actually achieve an equilibrium and it stays there. But you probably also realize that this equilibrium is extremely unstable. So if you don't place it exactly in the right spot, or if you have some sort of disturbance to the system, it's going to start trying to roll down one of the sides, and you have to, exert more effort in order to prevent it from doing that. So you have to be constantly vigilant and keep watch of what it is that's going on in order to be able to achieve your goal. Your goal is not something you only achieve, but also something that you need to keep on watching, whether it stays there. And one of the problems with that is, this is what I often feel it's like to be a software architect or a lead developer on a team, is you have to be constantly vigilant, because if you just look away for a moment, if you are sick for a couple of days, or if you go on vacation, or if you just go to too many meetings, what's going to happen is that you just let it go for a moment, and then everything rolls downhill again. And all the effort that you expended on actually getting to that goal, that is basically wasted effort now. And I feel like a lot of software development feels like that, or at least that's what it used to feel like for me. So I spent like at least a decade doing object-oriented design and being all sorts of, playing all sorts of different roles, from an individual contributor to a team lead to architect and such things. And I did this a lot, where I was constantly looking out for things that could cause the boulder to roll downhill again in order to try to prevent that from happening. And I sort of just I thought that was just what software development was all about. This was just an intrinsic part of the game, if you will. Then about 5-6 years ago, I started to learn about functional programming, and I got interested in this, in functional programming for a lot of other reasons. And the more I started writing, code with functional programming, the more I realized that a lot of these things that were very, very difficult in object-oriented design actually turns out to be quite easy to do with functional programming. It almost happens by itself. So again, if you can try to reimagine your goal and saying, well, it's not that you want to be on the top of a hill. That's not your goal. Your goal is just to reach an equilibrium. You can say, well, let's try to invert this and say, you just want to have an equilibrium. So you just roll your boulder down into the pit, and it just automatically rolls down and stays there. And even if you have a disturbance to the system, it's just settles back into the equilibrium again. So this is what we call a stable equilibrium. And this is really what functional programming feels like for me these days. And I just wanted to share a little bit with you why I think that is happening. So I should preface this right away by saying that this talk is based on my experience with writing F# code. So F# is one of those programming languages that have a nice logo, as you can tell, which makes it much more cooler than the other language. So a lot of these experience that I'm going to talk about here today is based on my experience with doing F# programming. And I've done lots of just playing around, fooling around with F#, but I've also written real production code that actually runs today in F# as well. So that is certainly possible. I'm also basing some of this talk on my experiences with fooling around with Haskell. And Haskell is a programming language that I don't have production experience with, but I've played around with for quite a bit of time now. I need to say that these two languages have a couple of things in common. They're both statically typed functional programming languages, and the type systems that they use are what we call a Hindley-Milner type system. And the reason why I say that this is that there are other programming languages, other functional programming languages out there that do not belong to this family of languages. Like a very popular one is Scala that runs on the JVM, which is also statically typed as far as I understand, but it's not a Hindley-Milner type system. And you also have something like Clojure, which is dynamically typed, and you have Erlang, which is sort of, I don't even understand if it has a type system or not. Every time I ask someone, they say, yes, it sort of has. And I say, what does that mean? It sort of has types. That's not really helpful. But anyways, so you may reach slightly different conclusions if you're talking about those languages instead of these languages, but these are the languages that I'm going to talk about. Right, okay, so let's see what we can do here with these things here. So I'm going to cover 3 pits of success. So the first one I'm going to cover is something called ports and adapters, and I'll talk about what that is when we get there. I'm going to talk about services, entities, and value objects, basically how do we think about data and behavior. And third, I'm going to talk about testability, which is really fun to talk about. So it's not that I've only identified 3 pits of success during all these years of working with functional programming. I've actually identified like 8 or 10 of them, but I don't have time to talk about all of them. So I just picked the ones that I thought was the most important ones, and that is those 3. Right. So let's just dive right into talking about ports and adapters. So ports and adapters is a well-known, well-described software architecture, and it's a very it's a pretty good architecture for doing enterprise software. So I've written lots of code using the ports and adapters architecture. It has various names. So one of the names that it's known as is ports and adapters. It's also known as hexagonal architecture for reasons that remain unclear to me because it doesn't really look particularly hexagonal. And some people also call it the onion architecture because it has concentric layers just like an onion. And in a sense, you can say this is basically what we know as layered application architecture done right. So it's sort of like, it's a little bit of that also, but it's related to that sort of architecture. And I'm not trying to tell you that this architecture is bad. I'm just going to tell you that my experience with this architecture is that in OOD, it's difficult to achieve. But actually, the goal is great. I really like this architecture because it solves a lot of problems. Basically, what we're trying to do with this architecture, we're saying in the middle there, the boxes in the middle represents your domain model, your business logic. This is the stuff that you actually care about. This is why you're building the software, because you have some sort of business logic that is important to automate. So this is actually what ought to, deliver value to your organization. And then you have, layers that protect that, because you need that business logic to, interact with all sorts of real-world systems. Like you need to draw graphical user interfaces. You need to write things into databases. You need to send emails and all of those sorts of things. But you don't want your business logic to be too dependent on all of those technical concerns, because they may change. So you want to protect, the valuable parts of your software from all the incidentals, all the technical details. So that's basically what this sort of application architecture tries to achieve. And that's perfectly fine. My experience with this, though, is that it's like rolling that boulder up the hill, is that in the sense that it's really difficult just to explain to a team of software developers who've never heard about this before why you would want to do this. Because it goes into a lot of things about, the design principles of object-oriented design, like the solid principles, for example. And you need to think about dependency injection. And you need to think about all of these things that, in order to understand those things, you have to read thick books about it. Robert C. Martin, who is the original person, or the person who originally described the solid principles, he has a book called Agile Principles, Patterns, and Practices. And this is a 700 pages long book that describe the solid principles and gives you examples of how that is and why it's interesting and so on. And I wrote a book about dependency injection, which I think is a good book, but it's 500 pages. And the book these books are so big should be a telltale sign for us to say, well, if we need that many pages to explain a concept, maybe we should start to think about if there's a better way. Is that really the best we can do? So the first problem with this is that it really takes a lot of effort just rolling the boulder up the hill, in the sense that you need to make everyone on a team understand why it's important. But then once you're there, it's even more difficult to stay there, because every small disturbance into the system might actually destroy the entire system. For example, if I go on vacation or just sick for a couple of days, maybe what's going to happen then is that there's some urgent issue in your production system that you need to address. So you go in and say, well, in order to address this urgent issue, we'll just call the database directly from the domain model, because we know that we can't do that, but we'll fix it later, okay? And you know that later is never. And that just causes this thing to unravel very quickly again. So it's not really particularly stable. So it's not that it's impossible to do with Java or C#, but it's really, really difficult to do. Now, what about functional programming? Does functional programming help? And it does. Let's try to understand why that is. But basically what I'm saying is not that the architecture is bad, but basically just that it's difficult to achieve this architecture at least with the object-oriented languages that we normally use. Whereas with functional programming, it sort of tends to fall into this sort of architecture all by itself. So let's try to understand why that is. So let's start to talk about what is the design ideal of functional programming. Well, in functional programming, we really like these things called pure functions. And why do we like pure functions? We like pure functions because they're easy to reason about, they're easy to manipulate, and they are easy to compose, and they have all sorts of nice qualities about them. It also turns out they're easy to test for reasons that I'll explain later. So we really like our pure functions. That is the design ideal of a function, functional programming code base. So what is a pure function? We need to understand that. A pure function is a function, first of all, that is deterministic. It always returns the same output if you give it the same input. The other thing about a pure function is that it has no side effects. A side effect may be that you send an email. It may be that you write files to disk. You delete a record from a database. It may also just be that you change a value in memory. So it might not be something that involves I/O, but anything that is observable from outside of the function. If it changes the state of something outside of the function, we call that a side effect. So it needs to do neither of those. It can't do side effects. It can't do non-determinism. If it's deterministic, has no side effect, we call it a pure function. So you probably go then, but side effects, all software development is basically all about doing side effects. When we create software, we want to print new UI on a screen of the user. That's a side effect. We want to send off emails. That's a side effect. We want to put things into a database. That's a side effect. Why would we ever how would we ever be able to do something if we can only do pure functions? And we never say that you can only do pure functions. We just say we like pure functions, so we want to maximize how many pure functions we have. But we absolutely acknowledge that we also need to have impure functions because we need to write to databases, we need to update your user interface, and we need to do all of those things. We just say we prefer the pure functions because they're easier to develop, they're easier to maintain. So there's a couple of relationships between those two things that you need to understand. And first of all, if you have a pure function and you want to call another pure function from that pure function, that is absolutely okay. You can do that. It doesn't make your calling pure function more or less pure that it calls another pure function. That's just a way of composing things. Makes absolutely sense. If you have an impure function and you want to call another impure function from that impure function, you can absolutely do that. It doesn't change whether it's more or less impure. That's possible. You can also call a pure function from an impure function. If the function is already impure, it doesn't become more or less impure by calling pure functions. And pure function is something as simple as 2 plus 2. So you can definitely do 2 plus 2 equals 4, even though you're in an impure context. You're trying to save something into the database. That's absolutely possible. Going the other way, on the other hand, is not possible. And there are various ways it's not possible. In Haskell, for example, it wouldn't even compile. I'll show you what that looks like in a moment. In F#, it's not that you can't sort of do it. If you imagine that you have a function that's pure at the moment, but then you want to change the implementation a little bit, and the change you introduce is a call to an impure function. What's actually going to happen then is it will compile, but that your function that was pure before now also becomes impure because it's calling into another impure function. So it just moves from one place to the other one, you could say. So you can't go the other way. You can't call impure code from pure code. That's really important. Let's try to see an example what that would look like and why that is important, because this is basically the explanation for why we tend to fall into this ports and adapters architecture when we do functional programming. Right, okay, so let's look at an example. So one of my favorite examples is a scenario where you try to implement a system for doing restaurant reservations. So these exist already, but this is just to, it's a nice, rich problem domain, so it's nice to talk about. So you imagine that you want to make a reservation on a restaurant. You go to a website or an app, fill in some details, and then you hit a button to send off your reservation. And in this particular scenario, what we can imagine then is that there's a JSON document that your user interface somehow posts to an HTTP-based server, and the HTTP-based server receives that JSON document and wants to deal with it. So we'll go through 5 steps here. The first thing we need to do is to validate the incoming JSON, because JSON is not particularly strongly typed. So we'll need to validate, is it actually well-formed? Do we understand what is being said here? If it's valid, we can move on. If it's invalid, we'll need to return a response. We'll get back to that later on. But imagine that we've determined that this is a valid, well-formed JSON document. It means we understand what it's trying to say. It means we understand the date on which the reservation is being attempted. And that means also we'll need to look into our database to say how many existing reservations do we already have for that date? How many reserved seats do we have from that date? From that date. Let's read that from the database. Now we have enough information to make a business decision. Do we actually have enough excess capacity to accept the reservation? If we have, we can save the reservation into the database so that it becomes part of the decision when the next request comes in. We might be short-circuiting various ways in various steps here, because if we can't validate, there's no reason to go through the rest. If we decide that we can't accept the reservation, there's no reason to save it into the database. So we might short-circuit at various points, but I'm not showing those arrows. But what we might want to do anyway, independent of the decision we reach, we want to say, well, let's translate our decision back into an HTTP response that can then be sent back to the client. So those are the 5 steps that we need to go through. And you will notice that 3 of them are green and 3 of them are not red, but purple. And the 3 obviously are the pure functions, and the purple ones are the impure functions. But you'll also notice that they're sort of interleaved. So we have those 3 pure functions, and we have those 2 impure functions, and we somehow need to make them mix them together, and we'll wonder how we can do that. So let's try to look at what that would look like. So I'm going to show you some Haskell code, and I'm not assuming that you know Haskell at all. What's really important here is just the top line. So actually, everything but the top line is the only reason why. So the top line is the function declaration and its type, and the rest of it is actually the implementation of the function, all the whites and so on beneath that. And you don't really need to read that. Just read the top line here. I just put the function body there to show off that I can actually write Haskell code. So, haha. But it's not important. Let's look at the top line there. The validate reservation, the blue and the orange stuff here. So validate reservation just declares, here's a function, its name is validate reservation. The orange stuff then is the type of the function. It says, it takes something called reservation rendition as input. This is sort of our Haskell representation of the JSON document. It returns something called either error reservation as output. It's not particularly important exactly what that means. What's important here to realize is that this function is pure, and it's guaranteed by the compiler to be pure. Why? How do we know that? Well, basically because in Haskell, all functions are pure by default. So unless explicitly stated otherwise, they are pure. And this one does not explicitly state that it's impure, and therefore it's pure. And because the type is declared as being pure, if I tried to do something in the function body there that was impure, it wouldn't compile. But I'm not trying to do something impure in the function body there, so this compiles, and it's fine. Now, what does it look like if we want to explicitly state that a function is impure? Well, it looks like this. So I'm just going to show you a function declaration without its implementation. So this is the next function in that little sequence diagram that I showed you, get reserved seeds from DB. So it takes a connection string and a zone time, that's basically just a representation of the date, and then it returns something called IO of int. And this is impure, and the reason why we know that is because those two letters, IO, indicates that this is an impure function. So basically what is it returning? IO of int. Int is just an integer, so it returns the number of already reserved seeds for that zone time. But that integer originates from an impure context, because it's not deterministic. Reading from a database is not deterministic. You could read from a database, calling the same database query twice, and you'll get two different results because the state of the database changed in the meantime. So that's not deterministic. So that is an impure operation. But basically what IO of int says is that there is an integer, but it's packaged up inside of an impure context. So you can almost think about this impure context as being sort of like a little bubble or a little space that it is sort of, sits around that integer. And when you're outside, when you're in a pure context, you can see the bubble or box or whatever you want to call it where that integer is inside, but you can't see what the integer is. So it's a little bit like Schrödinger's cat, maybe. I don't know. Not really. But anyway, so you know that you have something that contains an integer, but as long as you're in a pure context, you don't know what that integer is. So how do we get that integer? I'll get back to that. But I talked about how you can't call an impure function from a pure function. But I'd like my business logic to be impure because basically I just like as much as possible of my code to be pure. So I want to be able to make a decision. So I could write a new function called check capacity, and I could just, if I just for a moment forget about this distinction between pure and impure, I could say, well, in my ideal dream world, I'd like to have an integer which represents the number of already reserved seeds. And I also need an integer that represents the capacity of the restaurant. So that might be just another number, like the restaurant can hold 10 people, or it can hold 100 people, or whatever. So I need those numbers, and then I also need the reservation itself. If I have those three pieces of information, I can make a decision. That is a pure function. How do we know that? Because there's no IO involved in the type declaration there. So I'm sort of just brushing aside that I don't actually have an int for the reserved seeds. I have an IO of int. So how do I get it out? Well, I'll get back to that, but it turns out to be possible. But if I did that, though, if I decide to accept the reservation, I could say, well, all right, let's save the reservation into the database again. Now that is another impure operation. We can see that because it returns IO of nothing. Those empty brackets there, we call those unit. And both F# and Haskell has this thing called unit, and it's basically void like it ought to be, because unit is a real value, so you can use unit as a return value, but you can also use it as input. So you can take a return value and pass it on as input to another function if you need to do that. And that turns out to sometimes be interesting to do. But if you think about those empty brackets as being sort of the same thing as void in C# or Java, you know that if you have a method in C# or Java that returns void, it pretty strongly indicates that there must be a side effect of calling that method, because why would you call a method that doesn't return anything? You probably want to achieve some sort of side effect. So that's possible also in Haskell, but it's only possible to have side effects in an impure context, because side effects are per definition impure. So we have IO of unit. Now the final thing we need to do is to say, well, if we've reached a decision so far, we want to translate it back to an HTTP result. So we could do that as well. Again, you just look at the top line there. We can see there's no I/O involved in that, so that's a pure function as well. This is just a translation from our internal representation of, did we accept the reservation or not, and then just something that we can translate to HTTP responses that can go on the wire. That's basically what we're doing here. All right, so we have those 5 functions. I wrote 3 pure functions, 2 impure functions. I somehow need to, again, interleave those so that they can all talk together, because I need some of the impure information in order to continue with some of the pure, the pure operations. But I said I can't call pure functions. No, I can't call impure functions from pure functions. So how do I resolve that issue? Well, it turns out that at the boundary of the system, every system is impure, because when you get a request coming into a system, or someone presses a button on a user interface or whatever, that is non-deterministic side-effective behavior anyway. So everything that happens at the entry point of a system is by definition impure anyway. So we could imagine that we have some sort of entry point where we could say, well, if we put all of those functions into some sort of web framework, we could imagine that we have some sort of framework that contains a dispatcher, and it says, well, all right, here's a JSON document that arrives at this particular URL. It ought to be dispatched to a function that can deal with that, and that is an impure function. So we need to have an impure function that can deal with an incoming request anyway. So let's use that function to compose all of those other things together. So in this case, I've just called it post reservation. And if you look at the top line again, the orange stuff, you can see it takes reservation rendition as input, returns I/O of HTTP result of unit as output. So very clearly, this is impure as well. This has side effects or non-deterministic behavior inside of it. And that means we can do everything. When we're in impure context, we can call pure functions and impure functions. So we're pretty much almost there, and we can just walk through a couple of the details. So don't worry about all the Haskell-y scary stuff, like all the strange-looking arrows and dollar signs and so on. That's basically, you can think about that as glue that enables you to compose functions together. And I'm not going to walk you through all of it, but basically just if you look at the, you can see there are 4 indented lines. If you look at the top indented line, the one that starts with R, arrow, hoist either, and so on, you can see after the dollar sign it says validate reservation candidate. That's a function call. The validate reservation was the first function that I showed you, and that's a pure function. And it returns a value, and we do gluey stuff to that value in order to be able to address it later on. And then if you look at the next line, you can see there's more Haskell googly-gook there, but after the dollar sign it says get reserved seeds from DB, and a couple of input arguments to that. And so again, I'm in a pure context. I'm inside of the impure bubble, if you will. So that means I can call both pure and impure functions, or everything goes here. And that means now that I that sits on the left-hand side of that arrow, that is the result of calling get reserved seeds from DB. And you saw before when I declared the function, I said it returns I/O of int. But I'm now, opened the door and went inside of the I/O context, and that means the I is now no longer an I/O of int, it's just an int. Because I'm already in the impure context. And that means I can pass that as an argument to check capacity. So that's the next to last line there. It says hoist either, more Haskell gobbledygook, hoist either dollar, and then it says check capacity 10 IR. So 10 is just because I hard-coded the capacity of the restaurant. Very small, intimate restaurant, it can only seat 10 people. but then I is just the number of already reserved seats. That's just an integer at this point. So even if check capacity is a pure function, I'm calling it from an impure context, so that all works. And then there's some more crap going on there. Now, if we try to visualize what's going on here, we can try to draw it in with concentric circles. Funny how that works out. And so basically what happened here is you say, well, we get the incoming request. It's being dispatched to this function called post-reservation, which is an impure function. That's the one that I just showed you on the previous slide. Now, the first thing post-reservation does is it says, let's try to validate the incoming data. If we can do that, let's try to call the database to get the number of already reserved seats from the database. With that information, we can now call check capacity, which is another pure function. If we decide to accept the reservation, we can call save reservation, and then we can, no matter what we decided, we can return, translate things back into an HTTP result. And you will notice that I've drawn in the concentric circles, and you will notice that I've made some of the things purple, and I'll make some of the things green by purpose, because the green stuff is the pure stuff, and the purple stuff is the impure stuff. And it has to be like this in Haskell, because it's the only thing that compiles. Because I have this constraint that I can't call impure code from pure code. I have to structure my data, my application in this way. So you will often hear Haskellers talk about, I/O happens at the boundary of the system. Yes, because Haskell, forces you to do it in this way. And there's no other way you can actually do it. But if you sort of look at this a little bit, you'll see that that is very, very close to being ports and adapters. This is basically the ports and adapters architecture. In the middle there, check capacity, that is my business logic. In the concentric circle around that, validate reservation to HTTP result. This is what you'd call your application model or your service layer or whatever people tend to call it. This is where you adapt your business model to the outside world, and then you have the impure stuff on the boundary there. And you could even imagine if you just slice it through horizontally, through the middle, you basically have, your normal horizontally layered application architecture, because you have your interface to the outside world on top, and then you have your application layer, then you have your domain model, then you have your data access layer there in the bottom. So you can almost imagine that there's sort of a can, shape, sitting down here that represents your database, and then you have, your horizontally layered application model there. But the thing is, it just automatically falls into this model, because that's basically all it can do in Haskell specifically. So if I was a team leader on a Haskell project and I went on vacation, and then you had the same sort of urgency as before, where you say, I really, really want to call the database from within my domain model, from within check capacity, because I really need to solve the problem fast. You could try to do that, but basically that would mean you can only do that if you change the type of the function to become impure. And changing the type of a function is a breaking change. And that means now all the rest of your code is not going to compile. And at that point, it might actually be easier to actually do the right thing instead of trying to fix all those breaking changes. So it really just helps you to do the right thing up front. And you can do the same thing in F# as well. F# is not so strict about its distinction between pure and impure, but this is basically the same composition as I showed you in Haskell before. It doesn't really enforce it, but there are ways that you can do that if you're a team lead or a software architect on an F# project, and it's not particularly difficult to keep track of whether you're doing the right thing. F# sort of tends to fall into this way of writing things fairly easy as well. I have a blog post that shows all of this code if you're interested in that, so you don't really have to take a lot of notes. If you really want to dive into it, I have that on my blog. On my blog, and if you can't find it, then ping me on Twitter. Right. So that's really nice that we sort of just fall into this pit of doing the right thing, having the right software architecture all by itself. So let's move on to talk about services and data. Now, when people initially learn about object-oriented programming and object-oriented design, they they are often taught that objects are data with behavior. And there's this concept called encapsulation that says you should not really expose the internals of your objects. What you really should do is you should have your objects expose enough operations so that a user of the object can just ask it to do things, tell, don't ask, if you will. So that's this whole idea about, this whole design idea about encapsulation and object orientation. And if people are, new to enterprise development and they're just out of college or wherever they, learned object-oriented design, they probably come out and they'll do designs like this. So they say, I need to keep track of a user in my system. I have lots of users in my system, and the users have ID. They have an ID and they have a username. I also need to persist my user in a database. So I'll do, create, read, update, and delete that can talk to my database. And, this is a well-described design pattern. It's called active record. And if you read Martin Fowler's book, Patterns of Enterprise Application Architecture, it's actually described in that book. So it's sort of like, almost seems like this is some sort of well-known good thing. But it's turned out that, in the last decade at least, we've pretty much experienced and learned the hard way that this is probably more of an anti-pattern than it is a pattern. At least in C# and in Java, it seems like it still does some good things in Ruby, I don't know. But Ruby is dynamically typed, so maybe other rules are at play there. So I'm not pointing fingers at Ruby at all, but I'm just saying, well, I'm talking about statically typed languages here. At least in C# and Java, we've learned the hard way that that is actually not a good way to design systems, even though this seems very object-oriented. A user is an encapsulation of data about the user together with all the behavior that belongs to the user. This seems like object orientation. This, by principle, there's nothing wrong with this. But the problem is that you say, well, I need to do things with users, and later on you figure out I need to do other things with users as well, because I want to be able to send an email to a user. So I'll also add that, feature to the user object. And what often happens with these things is that the more behavior you add to a function, to a class like this, the more behavior it also attracts. So you'd end up with a couple of very, very big classes in a typical source code base that where the classes just attract more and more of this sort of behavior, and they become less and less cohesive, and we end up calling those big classes God classes, and that is a well-known anti-pattern as well. So we learned the hard way that this actually leads to something that is not particularly maintainable. So what should we do about it? Well, there's this book called Domain-Driven Design by Eric Evans, and it's sort of like two books in one. One part of the book talks a lot about this thing about actually thinking about the domain and the business language that you're trying to model and so on. But there's also a part of the book that is very concrete and talks about various design patterns and how to think about objects. And Eric Evans makes a pretty good distinction, very interesting distinction in this book that I think is very valuable, that have served me very well doing object-oriented design in the last 10 years at least or more. And he says, basically you can think about your objects as falling into two categories. And one of the categories has two subcategories. So basically he says, well, the first category of objects, we call those entities. And these are the objects that you learn about in university and so on. So if you ever had an introduction to object-oriented analysis and design, the question is, but how do I do object-oriented analysis and design? And the naive answer to that question is, well, just take the problem specification and just look for all the nouns, and the nouns will describe your objects. And we know that that's not really true, but there's some truth in that. Some of the nouns will actually be some of the entities you're interested in. Entities are objects that have, inherent identity, that have, long-lasting identity. So these are the business objects you want to keep track of. These are your users, your contracts, your orders. If you're keeping track of a fleet of cars, that is your car objects or whatever it is that you're keeping track of. These are entities, and you probably have those, and there's nothing wrong with that. And then he also talks about, well, there's another sort of object that also contains data, and we call those value objects, and that's another well-known design pattern. But basically what Eric Evans then says is that these objects are basically just carriers of data, and they don't really encapsulate any business logic, because we've learned that if we try to put business logic inside of these things, business logic changes. So it's not a good idea to put business logic that changes, at a different, cadence that the data changes. It's not a good idea to put those together. So instead, you should put your business logic into collections, other objects that are collections of behavior, and he calls those things services. And you probably, heard lots about, services. This is basically just another word for manager. So you have like your user manager and things, and all of a sudden you also have your manager factory service and so on. But that's basically the stuff that he's talking about here. So what does the user that we looked at before, what does it look like if we refactor it to do what Eric Evans tells us to do? Well, it looks something like this. So we'll say, all right, here's a user. It has an ID and a username. And I even went to the effort of making this immutable, which I hadn't needed to do, but I just wanted to do that. And that's it. It's just the data. And then we can say, well, what if we need to create, read, update, and delete operations on that? Oh, well, for that we have the repository pattern. So you can have like your SQL user repository class that implements iUser repository that does all of that. Now, that's another well-described design pattern that everyone, by the way, gets wrong, but that's a different story. And if we want to send emails, we can have another service that does that, email sender. So my experience with doing this is that that actually works. If you need to do object-oriented design and development of a maintainable, non-trivial system, this actually works. This is a way to keep a code base maintainable for years. But the problem, again, is you have to read thick books in order to understand why you have to do this and how to do it, and you need to get everyone on the same page. So again, we're a bit of that situation where it feels like rolling a boulder up a hill. And again, if you look away for just a moment, then someone comes by and totally ruins everything. And then you're back to start again. And not even that, but also you'd say, but that's not really object orientation anymore. This is an anemic that's an anemic domain model, right? That's a very common criticism of this sort of code. It says, well, that's actually not object-oriented code anymore because you've separated data from behavior. That's not what object orientation was originally about. Or maybe, everyone tries to second guess what Alan Kay meant when he coined the term, but I don't know. But basically what we taught about, C# and Java, that's not the sort of object orientation we were originally taught. So what about functional programming? Does it make it better? You betcha, because functional programming basically wants you to do this. It says there's data and there are functions that operate on data, and that's it. That is how you are supposed to work with your stuff. This is how you are supposed to write code in functional programming. So if we look at this same example again, we can say, what does a user look like? This is an F# example of a user. It's just a one-liner. It's almost declarative. Well, it is declarative. You say a user is a type that has an integer ID and as a string username, and that's it. This is a strongly type declaration, but it has no behavior. And, well, in F# you can add behavior because F# is what we call a multi-paradigmatic language. So you can make it more object-oriented if you want to, but you shouldn't really feel the urge to do this. This is fine. This is what it wants you to do. In Haskell, for example, there's a little bit of a different syntax of doing this, but it's basically the same concept. And in Haskell, you can't add any behavior to data. Data is data. It can be as deeply nested and very, it has a very complex structure, if you will, but it's just data. It has no, associated behavior. So we should feel good about this. This is not anemic or anything. This is how functional programming should look like. And if we want to do things with the user, if we want to save it into a database or something, we can create a module, which is a collection of functions that either, take user as an input or return user as output, or maybe even do both. I don't know. These are impure, by the way, but that's not really the point. But the point is, a module is basically just a service, but it doesn't have to pretend that it's an object because it's just a module. And you could have a module for sending email as well. So that's basically just what F# wants you to do, and this is what Haskell wants you to do. So it wants you to do what Eric Evans spends 400 pages trying to teach you how to do. This is basically, if you ever learned Haskell or if you ever learned F#, the functional parts of F#, this is what you are supposed to do. This is what the language wants you to do. So you're falling into this pit of success again, that's saying, well, these two things should not go together. They should be separate, but they can work with each other, and that's fine. Much more maintainable code base you get out of this. All right. So let's talk about testability, because testability is always fun to talk about. Kent Beck introduced the concept of test-driven development back in mid-90s, so 95, 96, something like that. I can't remember the exact date. And it was really, really controversial when he started doing that. And I picked a test-driven development up in around 2003. It was really, really controversial back then. There's been more acceptance of test-driven development now to the degree where most people actually seem to think that it ought to be. That's actually a well-known best practice now. But it turns out it's still sort of controversial. And from time to time, the controversy pops up again. So a couple of years ago, David Heinemeier Hansen wrote an article called TDD is dead, long live testing. And basically what he, I'll try to cover what he said in a moment, but basically he said, well, it's not that he's against testing, but he just thinks that test-driven development actually leads to a lot of problems. He leads to what he calls test-induced damage. Now, David Heinemeier Hansen can be quite controversial himself, and some people really don't like his style because he's swearing a lot and he's saying things in a very provocative manner. But I've found over the years that if you actually try to listen to what it is that he's trying to say to you, he's really a free-thinking spirit. He does not just go with the flow. He goes against the grain, and sometimes it seems like he makes an effort out of doing that. But basically, if he says something that goes against the grain, it's worth the effort at least to try to understand what it is he says, because he's a very intelligent young man. I can say young man now because my hair is gray. So let's try to understand what it is that he says. He says test-driven development leads to test-induced damage. That is his claim. I'm not saying it's my claim. That is his claim. Let's try to understand what he means by test-induced damage. So here is a class called capacity checker that tries to check the capacity of one of these restaurant reservation systems. So this is nice testable C# code. We have a class called capacity checker. It implements an interface called iCapacity checker. It uses dependency injection to have a capacity, that's just an integer, but also an iReservation repository, and we'll need to have the constructor in order to inject those in and save them in fields for later usage. Then we have on the bottom here Haskcapacity, which is the actual value that this class provides. It says, well, given a reservation, do we have capacity, yes or no, true or false? So what we do here on the last 2 lines of code there, we say, well, we'll ask the repository to get the number of reserved seats for that date. That gives us a number of reserved seats. Reserved is just an integer. And then we say, then we just do a comparison, a less than comparison, and says, well, if the capacity is less than that, what we already have reserved plus what is being requested, then the answer is false, otherwise it's true. So David Heinemeier Hansen's point here would be, why would you ever write code like that? The only valuable thing here are those 2 lines of code in the bottom. The rest is just noise. Why would you do that? And then you say, well, because of testability. All right, fair enough. So I'm not even saying that this is bad in the sense that, if you ask me to write a non-trivial, maintainable system in C# that has, test coverage, this is what I do, because I don't know of a better way of doing it in C#. So I'm not really pointing fingers at, I'm not saying this is bad practice. You may need to do this, but that is a high cost to pay to have, testability, because that really, it causes your code to be spread out instead of being, going well together, and it's difficult to manage and difficult to, navigate a code base like that, and you just have a lot of noise that you don't really need to have. What would it look like in another language, like in F#, for example? Now here's something, this is not even similar, because this actually does much more. It makes the same sort of Boolean comparison, but then it also, instead of just returning true or false, it actually returns a failure with some more information about the failure, if why it failed, if that's what's the case, and it returns success, if the Boolean evaluation returned true. So if I just wanted to do it entirely similar to the other one, just returning a Boolean, I could actually have done that in 2 lines of code, but now it turns out to be 4. Now this is, apart from that, this is exactly the same thing, because this is a function called check, and it takes 3 arguments. It takes a capacity argument, that's just an integer. It takes get reserved seats, which turns out to be another function, and then it takes reservation as the 3rd argument. So what you often see in functional programming is that you'll see functions taking other functions as argument. This is what we call higher order functions. This is a completely normal thing to do. Now, get reserved seats is a function. It plays the exact same role as that repository that you saw before. So on the first line, you can see it says, let reserved seats equal get reserved seats reservation.date. That is a function call. I'm calling the function get reserved seats with the reservation's date. And I'm getting out of that function call the number of already reserved seats. That function is just being passed in, and it's sort of polymorphic because I'm not asking for a specific function. I'm just asking for a function that can take a date as input and give me an integer as output. Any function that can do that fits that description, and that will compile. Now, is this function that we're looking at here, is that pure or impure? It turns out to be important in just a moment. So therefore, the question, is this pure or impure? Well, it turns out that most of the stuff that goes on up here is actually pure. The only thing we don't really know about is we don't know what get reserved seats actually does. So it may be pure, it may be impure. Now, if get reserved seats is sort of like the repository, like it's actually querying a database to get the number of already reserved seats, that's an impure operation because it's not deterministic. It depends on the state of the database. So in that case, it would be impure. And if it's impure, if that is a database call, then all of this function also becomes impure. That's how it works in F#. On the other hand, if get reserved seats is a pure function, then this function is also pure because there's nothing else in that implementation that could make it impure. Why is that interesting? It's interesting because it turns out that pure functions are always testable. And I'll get back to why that is, but let's just look at what would a test look like. What would a unit test look like of this function? Here's just one example. I'm only going to show you one example just to give you an idea about it. So the scenario here is that I want to test that it returns the correct result if there are no prior reservations in the system. So the system just booted up. There are absolutely no reservations. The restaurant just opened, and I want to check the first reservation that comes into the system. That's basically the scenario here. So I'm saying, well, I need to set up a little bit of context. I need to define what the context is. So I say, well, what's the capacity of the restaurant? I'm just hard coding that in this test case to 10 because, well, that's just an easy number to think about. I like the number 10 and the number 1 and so on. So that's just arbitrary, but it's just to have a test case. Then I say on the next line, I say let get reserved seats underscore equals 0. The underscore means that I don't care about the input. This is a local function. This is a function that only belongs to this test case. But it always returns 0 no matter what the input is. That is a pure function because it is as deterministic as possible. It always returns 0. That means there are never any reserved seats in this particular scenario. That's a pure function. And then I have this let reservation and then a lot of crap, with a lot of stuff. Yes, by the way, this is my email address. All the spammers already have it, so you might as well get it as well. So that's just, that's a little bit, that looks a little noisy because there's actually a lot of code there, but it's just data, and we could put that in some sort of factory if we wanted to do that, but I'm just showing you a self-contained example here. And then, on the third to last line there, it says let actual equal capacity check, capacity get reserved seat reservation. I'm taking those 3 arguments that I set up in a range phase and just passing them as arguments. I'm getting an actual result back. I can now declare what did I expect and compare those 2 things to each other. And this test will either pass or fail. That was easy. So you might wonder now, is it coincidental that this was easy to test? And it turns out it's not. There is a reason why this was easy to write. And the reason is that as long as a function is pure, it is intrinsically testable. And let's try to understand why that is. In order to get help to understand that, let's refer to Jessica Kerr. Jessica Kerr sometimes talks about a concept that she calls isolation. And she says, isolation is, when the only information a function has about the external world is something that is passed into it via arguments, then the function has isolation, and that is a good thing, by the way. This is a desirable quality of a function. So basically what we're saying is a function does not have any implicit knowledge about the outside world. Everything it needs to know in order to do what it is that it wants to do needs to be passed in as arguments. Now, is a pure function isolated? Yes, always, because a pure function must be deterministic, otherwise it's not pure. And by deterministic, we're saying it should always return the same output given the same input. It is only the input that can influence the output of a function. So therefore, a pure function is a subset of all functions that have isolation. The F-sharp function that I just showed you may not be pure. We talked about that, but it has isolation because it makes no attempt of, using it, implicit knowledge about the world. Everything it tries to do is based on its function argument. So it has isolation. It may not be pure. Maybe it is. We don't know. But at least pure functions, the ideal of functional programming, all pure functions have isolation. Why is isolation interesting? Let's talk about unit testing. Why is isolation, important in the context of unit testing? Well, let's try to see if we can come up with a definition of unit testing. Basically, if you have 10 experts in unit testing and you ask them to come up with a definition of what a unit test is, you'll get 12 answers. So it's not really possible to get one definition of a unit test, but here's one that I use. A unit test is an automated test that tests a unit in isolation from its dependencies. And most experts in unit testing, where they disagree is, where all the controversy is it means it's basically around what is a unit. And I'm not particularly interested in what a unit is. The thing that I'm interested in this definition is the word isolation. We want to test the unit in isolation of its dependencies. This is the same sort of isolation that Jessica Kerr talks about. All right, so let's try to understand why, why David Heinemeier Hansen may be up onto something and why it's not a concern in functional programming. So David Heinemeier Hansen says, well, isolation is an important quality of your code if you want it to be testable. And then, you try to combine that with object-oriented programming, and bang, you have test-induced damage. And where I think that David Heinemeier Hansen draws the wrong conclusion, he says, and that's the fault of test-driven development. Whereas I'm more and more beginning to see I can do test-driven development with functional programming, and it does not lead to test-induced damage. So therefore, the problem must be somewhere else. And I think actually OOP is the problem. So let's try to understand why object-oriented programming is a problem here. Now the design ideal, the philosophy behind OOP is encapsulation. This is what we're aiming for. This is what we were taught is important in object-oriented design. If we want to be testable, we now need to aim for this quality of isolation, because otherwise it's not really testable. Now, again, we're in this situation where we're trying to roll a boulder up the hill. It is possible to sit there in the intersection between those two sets and say, here's testable OOD. It is possible. But again, it requires a lot of effort, and it requires a lot of diligence and a lot of constant monitoring of what's going on, because otherwise you'll probably err to one of the sides. And what's often happening is if you don't have a focus on test-driven development or testability, you may err to the side of encapsulation. That's basically what happened the first 10 years of the .NET framework, for example. The first 10 years of the base class library in .NET, it was infamous for not being particularly testable. It's much better now, but it was really difficult to test base class libraries the first 10 years of the .NET framework's lifetime. Now, on the other hand, if you are focusing on test-driven development, you often err to the side of isolation. And then you get something that is, that has this test-induced damage that David Heinemeier Hansen talks about. But in functional programming, it's different. Because what's the ideal function in functional programming? Well, it's that pure function that we already talked about. That is the design ideal. It has isolation. And because it has isolation, it's testable. There may be other ways to make things testable, but if they have isolation, they tend to be testable. but there is no, there's no intersection that you need to fit into. Basically, if I had a team of, developers who are already good at doing functional programming, I could basically just, say to them, if I was the lead developer or software architect, I could say, just write as many pure functions as you can. Do good functional programming design. Write pure functions. And I'll go on holiday, and I'll come back, and then we'll see, then we can start testing it. That might actually be possible, because if they write pure functions, they are testable. So what I've tried to do here in this talk is to talk about, in my experience, there were lots of things, more than 3 things, that I've experienced during my career as architect and lead developer and so on, where I say, this requires a lot of effort. This is really difficult to do in C# and probably also in Java. But it turns out that if I try to rephrase the way that I approach my things and use functional programming instead, all of these things just sort of automatically fall into a successful place. It just automatically happens. So we looked at 3 things. We looked at ports and adapters. We looked at services, entities, and value objects. We looked at testability. All of these things turn out to work very well. It's not the only 3. I know of others, but I didn't have time to describe any more. If you want to know more, then, well, you can come and talk to me afterwards. I will not have time to do Q&A right now, but I'm happy to talk to you afterwards. Otherwise, you can also visit my blog. I blog a lot about these things. I also have Pluralsight courses. I have Pluralsight courses on test-driven development, unit testing, functional programming, all sorts of things. And since I go under the pseudonym Plur, I just created this bit.ly/Pluralsight. So that's just a link to all my courses. If you don't have a Pluralsight subscription, you can come and get a voucher. I'll get it out in a moment. I have vouchers that'll give you a 1-month trial subscription to Pluralsight for free, so you can come and get those if you need them. But otherwise, I'll let you go for lunch in 10 seconds. I just want to say, if you have questions, then come and talk to me now, or in the hallway, or if you see me around in the conference, or send me an email or whatever. I'll be happy to answer any questions that you have. But some of you want to go to lunch now, and I think you should do that. So thank you all for coming, and have a nice lunch.